talking about the ideal structure of Leavitt path algebras today. So I'll start with giving the basics again, just a reminder that Professor Armstrong has already mentioned. We start with the directed graph with the E0 to be the vertex set, E1 to be the range set, R and S to be the functions. SE denotes the source vertex of the edge, and RE denotes the range vertex. I'm going to consider mostly the graph to be finite, meaning that both the edges and the vertices are finite sets. However, it is possible that either E0, E1, or both may be infinite. However, we call E to be rho finite if this is the case, but no vertex emits. So I will consider graphs without any infinite emitters. A sink is a vertex which does not send any edges out. And I sometimes use this throughout the talk, so I wanted to give the definition. If a vertex emits at least one edge, but only finitely many edges, we call it a regular vertex. So it's not a sink, it's not an infinite emitter, anything else is a regular vertex. The set of all regular vertices is denoted like this. For any edge, we define E star to be the ghost edge, where you basically change the orientation. The range of E star is the source of E, and the source of E star is the range of E, as we have seen in the past. Let's remind you what the Leavitt path algebra is. We consider K to be a field, and E is this four tuple, a directed graph. The Leavitt path algebra is LKE with the coefficients in K. Is a K algebra generated by the vertices and the edges and the ghost edges, which basically satisfies those five relations. The vertices are idempotents. So if you multiply two different ones, you get 0. If it's the same, then you get itself, the idempotents, the orthogonal idempotents. SEE or ERE is E, so that is the concatenation. That's how you multiply the vertex with the edge. If it starts with it, it's basically E, and E times the range. And the ghosts, you extend it. Realize that the ghosts are oriented backwards. So the range of E is really the source of E star, so that makes sense. Same thing here. E star is times source E, which is range of E star, so it gives you E star. CK1 and CK2 relations is if you have two edges, that's how you multiply the two edges now. If you start with the ghost, and then you go with the real edge, this only survives only if E and E star are exactly the same, and then they move out or simplify to the range of E. Any vertex V, the CK2 condition, is the sum of E star for every regular vertex V. So this sum is meaningful. You have V emits at least one edge, but only finitely many. So however many edges this produces, this sets, you basically sum E star and equate it to V. So that's the second relation with CK2. So that's to recall the definition of the Leavitt path algebra. If E is finite, then it's unital, the unit being the sum of all the vertices. However, if E is not a finite set, E0 is not a finite set, you have infinitely many vertices, then it's not a unital ring, but it's a ring with local units, which consists of the sums of distinct elements of the vertices. So the set of local units for this algebra is basically the sums of the vertices. To recall what a ring with local units is, a ring has a set of local units F. If F is a set of idempotents, we call the vertices related or idempotents, and so are the sums of the vertices. Having the property, if you take a finite subset of elements R1 through Rn of R, then you can find an idempotent, a local unit, U, in this set, F, such that URI is equal to RI is equal to RIU for every element here. So, depending on the finite set R1 through Rn, you can find a different U that satisfies this equation. A path is denoted by mu. The length is, a path is a finite sequence of edges. We denote from E1, it's starting from E1, E2, E3, En. So this, where the source of E2 basically is the range of E1, so I can basically concatenate. So if this is meaningful, if the concatenation makes sense, if you go from one to the other, and that's going to be a path. And the length of the path is the number of edges that basically it traces. So there are n edges here, so the path has the path. We consider vertices of length 0 paths. So vertices are a part of the set of all paths in the graph E, which is denoted by path of E. I'm just repeating this quickly from the first morning lectures. A path is closed. A path is closed if the source of the first edge is equal to the range of the last edge. So it starts and ends at the same point. And we call that the mu is based at the vertex S of the point. A closed path is simple if it doesn't pass through its space more than once. And if it's a cycle, if it doesn't pass through any of its vertices twice, Professor Ergasmami mentioned this in the morning, so I'll just go opposite. An exit is an edge that is not in the path, but it is basically emitted out from the path with another edge. That's not a part of it. So, I'll talk about a subset of E0, namely the hereditary subtree. Hereditary saturated sets are subsets of E0, the vertex set. Recall that if you have a path from the vertex U to a vertex V, we use this notation. We call U connects to V, but notice the relation. U is greater or equal to V is the standard notation that's used for this. So there is a path from the vertex V, from the vertex U to the vertex V. A subset H of E0 is called hereditary if whenever you have a vertex in the set H, and if there is a path from this V to any other vertex, then you want to make sure that that vertex is also in H. Then the set is called hereditary. And it's called, a hereditary set is called saturated. Now you go in the, if for any vertex V, which is not a sink, you look at S inverse V, this set is the set of all edges emitted from V. R of those edges are the targets, the endpoints of all the edges that are emitted from V. If all the targets are in H, then you come back and take V into H. So we start with the vertex, an arbitrary vertex in E0, and provided that everything, the targets of all the edges that V emits are in H, then you have to take V in your set. So let me give an example here. The hereditary and saturated sets will be important for us in determining the ideals. So if you look at the hereditary, if you have a vertex H, then and if B goes to W, then you want to make sure these are all in the set. Okay. Take this set. Now, this is not a hereditary set. The reason being, B is in this set, H is in the set. However, there is a path from B to U, which is not in the H. So this is not hereditary. Okay. Here I'll give a more interesting example. Now let's change the example to this one. Okay. Now, this set, I have B and W for this graph. Now this set is not hereditary again because I have B. From B I can go to W. From B I can go to U. But again, U is not in the set, so it's not hereditary. However, look at this one. Is this hereditary? Well, this is a sink. There is no way that you can go anywhere from here, so it's hereditary. Let me ask the question, is it separated? Now, yes. The reason being, vacuously it is, because, well, look at this set. I have W here. Let's take this as my third example. This is both hereditary and separated because there is no B that basically satisfies this equation in H2, so it's both hereditary and separated. Look at H3. This is hereditary. You have U and V that are both sinks, so that cannot go anywhere from those two vertices. It is a hereditary set, but it's not saturated. The reason being, now, S inverse of B for this set is basically, let's give this a name, E1 and E2 is E1 and E2. The R of S inverse of B is the range of E1 and the range of E2, which is U and W. Okay? Well, this is an H3. So according to the saturation definition, I have to be getting B in H3 if HD were saturated. Then B would have been, this is not possible. So that's why this is not saturated. Is that clear? I'll do another example which I'll probably use next class, so it's handy. So let's look at the, can you see the bottom part of the blackboard if I use here? All this U, this is a loop here, I call this C1. Two loops here, and two loops here. And all stuff. I have three vertices, U, V, and W in this graph. Let's look at all possible hereditary and saturated sets. Of course, there are two hereditary saturated sets in every graph. Call this graph E. Empty set doesn't have anything. It's a hereditary and saturated set. And E0 satisfies. So those are the trivial hereditary matrices.
I have one question.
Sure.
There you have written U and W, right? That's not hereditary. That's hereditary but not saturated. and W, na, that's what we do.
The H3 I picked to be U and W, correct?
But then,
It is hereditary, but not saturated.
but for saturated, U and W both are synced, na, according to your graph plotted there above.
Tell me again.
U and W both are synced, na?
Correct. It says for any vertex. This vertex can be a sink.
Which is
Oh,
not a
this
sync.
vertex is not a sink. I'm sorry. Go ahead. Go ahead.
So U and W both are synced, na, there in your graph.
Correct. Yes.
So it's then means as a empty set it would be saturated, right? Or I am missing something.
Okay. The vertex V is exactly. Look at the V here. So that's the candidate. I'm trying. I have U and V in my set. I am trying to see if I can go backwards and take this set. If this vertex is in H3, then it would have been saturated. The reason being, look over here. Now, the S inverse of V are these edges, right? U1 and U2. And the ranges of that is U and W. But U and W is in H3, so it satisfies this, right? Then it implies V is in H. I have to have, this is satisfied, however, V is, well, I shouldn't say that. If H were saturated, then this condition would have implied V is in H.
So this condition has to be checked for every vertex?
Correct. Correct. Okay? I have to check for every vertex that if R of S inverse of V is contained in the set, V is also in the set. Then I can say H3 is saturated. However, this V is not in H3, so this cannot be. This fails. That's the story. Go ahead.
Yeah, so I think he's right. So he's saying you have to check it when it's not a sync. And both the vertices you are taking are syncs. So this condition should not be checked for those times.
No, it has to be
V
checked.
is not a sync because it emits edges.
If you had a sync, it would be the empty set, and
Yes.
it would automatically be
Yeah,
a subset,
exactly.
so you don't want to worry about that.
Exactly.
But B is not a sync.
Q and W are syncs.
Correct, but there can be elements here which are sinks. But
Oh, sorry.
It has to be checked for
okay,
every vertex.
but V is not a sink because it emits something. Okay. Well, let's see how many hereditary saturated sets we have here. Look at the vertex U. Is it hereditary? Well, I have 3 vertices, so don't have that many conditions anyway. U is not a sink if there is a loop, but U just gets into U, so this is hereditary. Is it saturated? Now, is it possible to go back and get W in the set? No, the reason being because W has edges whose ranges are W and also another one here. Well, unless these 3 were in the set, I wouldn't be able to get W back. So this is fine, it satisfies. This is both hereditary and saturated. I don't have to worry about getting W in my set because W emits other edges whose ends are not in my set edge. So it is saturated. Okay. How about E? Same idea. It's hereditary and saturated. How about W? Huh? Is W hereditary? No, because you can go from W to both U and V, so it's not hereditary. Once you have, in a hereditary saturated everything in. Okay? Well, so we already covered it here, so I don't have to worry about that. If you're taking notes, I'm going to keep this as H1 and H2. Well, so how about U and V? If you take U and V, that's also hereditary and saturated. The reason is that I have W that goes as loops there. So this is another hereditary and saturated set. I'll call this H3. Okay. So that all possible hereditary and saturated sets, subsets of this set. Okay. Let's move. Now, the reason we mention this is there is a relation between the ideals and the vertices. And if E is a graph and I an ideal of the Leavitt path algebra, then once we intersect the ideals being two-sided ideals, I'm always going to talk about two-sided ideals. An ideal intersected with the set of vertices is going to be a hereditary saturated set, which can be an empty set as well. Let's look at the proof. If you take any vertex in the intersection, I have to prove that this set H is actually a hereditary saturated set. So if U connects to a vertex V by a path P, I have to prove that V is also in H. By the CK1 relation, if you have the path P, then you can multiply that from the left by P star. But P star P, recall that P goes to V, and then you go backwards with P star. However many vertices edges you have here, then you go back via the ghosts. These are the ghosts. So what happens is you have E1, this is E star. So if I want to write this diagram, then this is going to give you star. No, there. And then you're going to have EU. Oh, yes. EU1, I'm not. And then you go ahead and, of course you can't see there anything, so why don't I write it here? EN star, E1 star, that's E star, and then I have EN, that's P. So CK1 says, each time you have an H star with itself, then you can take this and put it range of E1. Well, range of E1 then starts with E2, and I have E2 star range of E1, E2, but this is the same thing as source of E2, so that just simplifies. So you reduce to one edge, one term there, and then you get this. This one gives you range of E2, which is the source of E3, so that cancels out. In a similar manner, finally you get the range of En, which is the range of, which is a vertex, and that's exactly the vertex we write here. This was my original graph. So that is here. Okay? And so B is this guy, which is equal to, recall that right here we have the vertex 2. So it is basically in the ideal. So V is in the ideal, so H is hereditary, I can do this. So CK1 helps me to prove that this H is hereditary. Now, to prove it's saturated, I'll need CK2. V is a regular vertex, assume it emits and edges, and all has the ranges to be VI, and all of them are in H. Recall, that was the condition. So the ranges of all the S inverse of V are in H. So that's the condition. If this is satisfied, I have to show you that V is an element in H. V is in H. Okay? But CK2 saves our life. That's exactly the second relation because V is equal to, here you have V, and then this guy emits and edges. V1, and all of these are in H. So V by CK2 relation is exactly E1, E1's EI, EI star, I goes from 1 up to 10. Okay? And this is nothing but this relation. Let's say EI, V, I, EI star. If this is an H, so is this. Hence, the sum is an H, so V is an H. So the element H, the set H is also saturated. Makes sense? Go ahead.
It seems like in the last part they were assuming that E is row finite.
Yes, yes, this is correct.
Okay, and if
The
the
graphs
graph
are talking about, I'm
is,
sorry.
is that a starting assumption?
Go ahead.
If the graph is not row finite, then is this theorem not true?
No, it is true. However, then
No, is that we use for infinite meters, but for saturated we just need to consider about regular vertex.
let me go back. I think
It's still clear.
go ahead. In the definition of the
For saturated we just need to take about
It's
the
true in arbitrary graph also because the condition applies only for vertices which emit finitely many.
yes, that's my mistake. I should have.
We don't deal with edges which are infinite emitters in the definition of a saturated.
Oh, okay.
I think I should. Ram, I think I should have said V is a regular vertex here. So that. Thank you for pointing out. Right? That molds it out. So V is not an infinite emitter either. It's not the same kind. Okay, so one quick example is maybe I'll get rid of there. Is this ideal that has come up in the morning and it will come up quite often. Consider this graph. We have seen that the Leavitt path algebra is isomorphic to Kx inverse. And we have seen that this is an ideal. This ideal generated by B plus X, so or in this terminology, the ideal generated by 1 plus X. Okay. However, one is not in this ideal. It's a proper ideal. So this is basically in this case. Okay. That's the hereditary and saturated set. It can be is, consider this, the Leavitt path algebra of this graph. It has two things. You have not mentioned this yet. I have two things here. The number of things tells you the number of subends I'm going to have. We have two things, so I goes from 1 to 2. And the number of paths that go into the sinks is going to tell me the number over here. It's an acyclic graph, so this is the number of paths that, and that W is W itself and this path, so that gives you 2. And similarly for V, you have another copy of M2. So this Leavitt path algebra is isomorphic to this. Well, if you consider the ideal, we can work this out as 2 copies of M2K. So consider this ideal. This is a proper ideal of the Leavitt path algebra. And this is going to give me basically, which is another hereditary set. I'll leave this as a question or a homework if you want to work out, because there is a nice homomorphism between the elements here and M2K. And this ideal is basically generated by the vertex W. So that's a non-zero hereditary set. Now let's go into the graded ideals. Give a definition of the graded rings. A ring is said to be Z-graded in case R is a copy of Rn's, where Rn's are homogeneous and homogeneous elements, and Rn is a subset of Rm plus n, for instance. An ideal is called to be a graded ideal in a graded ring if any sum of elements in A, where A can be written as a sum of the homogeneous components, then each homogeneous component is also an element of the ideal length. Or equivalently, you can say R intersection Rn, the homogeneous parts that in I constitute the whole ideal. Leavitt path algebra is a graded algebra. I'll skim through this. We have seen this in the morning. Each vertex and each edge has a degree. The degree of the vertices are 1. The real edges are the degree of each vertex is 0. I'm sorry. The degree of each vertex. Say it again. The degree of each vertex is 0. The degree of each edge is 1. Ghost edge is -1. So the real paths are with positive edges. And if you have a term of the form alpha beta star that we have seen, they are the ones that generate the Leavitt path algebra. The degree is basically, look at the alpha, the real part, the degree, the length of that path, minus the beta part. Beta and alpha being elements in a path, in the path of E. So I guess that's in red. Alpha, beta are the paths of E. For every n, I consider the homogeneous component of the Leavitt path algebra, and homogeneous component is the terms whose degree is n. So they are generated, they are of this form, where this should be I, alpha I, beta I star. The degree of each monomial is degree n. Ln is a K subspace, and then it satisfies this equation. So L is basically the path algebra is a Z graded algebra. Now, if I take any hereditary saturated subset, basically, the ideal generated by that will be the ideal of the form alpha beta star hats, whose the range of alpha is equal to the source of beta. So this is neutral. That's a mistake. This should be R
Range
of
of
beta. This should be source of beta star, or I apologize. That should be range of alpha is equal to the range of beta, which is the source of beta star. I apologize for those who cannot see what I've written. Okay, this should be a beta star here, or range of beta. That has to be in H, so this element is also generated and is in H. Now again, Professor Rangaswamy asked the question for the tutorial today. So the proof is relying on the fact how we can basically write the elements. If we compose one of these with another one, gamma delta star, that is going to be of the same form again. And that requires a simplification, so we can look at it. It is clear that if you have this set is always going to be a subset of the element in here, the converse requires that here, so it's not hard to do this. This is a graded ideal. It basically consists of the homogeneous elements, so it's generated by a set of homogeneous elements, hence it's graded. But however, there are no graded ideals, as the famous example again. This is an ungraded ideal. You have a degree 0 element here and a degree 1 element here. The sum is in the ideal. However, B is not in I, neither C. So I is not a graded ideal. Okay. We move it up. I have 15 minutes. Okay. Now, I'll define a quotient graph for a given graph. Take any arbitrary non-zero hereditary saturated set. We define the quotient graph denoted by H slash E slash H. It's quotient graph in E such that the vertex set is basically you get rid of the H and whatever is left. And then for the edges, you remove all the edges whose ends, whose targets, whose ranges are in E. So you leave the edges whose ends are. So that's the main theorem I'm going to discuss. Let me do a construction here with this one. If you want to define the quotient graph EEH1 for this one, basically I'll get rid of this part. So I'm going to erase this edge as well. So what I'm going to be left with is going to be that's the I'll leave this graph, so I'll put them all on. If you want to get rid of B, then you're going to get this down. And U here. So I got rid of the U part and all the edges that end in B. And finally, H3 will be, I get rid of the two tails. So I'm left with the Okay, maybe you go.
I didn't understand what was the vertex space. What is the equivalence relation quotient thing? I couldn't understand.
Oh, no,
what
the name is given. It's the name. It's called the quotient
okay.
graph. There is no equivalence relation. This is just a constructed, we are just constructing another graph from a given graph.
And then what is that E backslash H0? What is that?
Definition is it set? Just the definition of the vertices of E backslash. So she's defined the quotient graph to be this thing and defined the vertices in it.
Okay, so I didn't
There's no
understand what is a
equivalence
vertex.
relation.
Yeah,
Which is location.
so what is a vertex?
A vertex is a set, an element of a vertex of E which is not in H.
Okay. Even the later
It's
part.
not
is
a quotient and no group, no action there or no.
You take all the vertices here and then you subtract the H.
Okay.
Okay?
Yes.
So whatever that's.
Thank you.
Okay. Okay, let me give the theorem at least, and maybe I'll stop in a couple of minutes, and I'll continue next slide. Now, the main thing is there is a relation between all possible graded ideals, and there's a one-to-one correspondence, all hereditary saturated subsets. And when we take a row finite graph E, the condition row finite is necessary now. I'm not giving the generalization. There is a generalization for all possible graphs, but that requires a little more than hereditary sets, so I decided not to overwhelm you with the details. I denote by the set of all graded ideals with this. It's a lattice actually. It's a poset with respect to inclusion, but it's a lattice as well. So I'm going to give a few examples of different lattices, the Hasse diagrams of both the hereditary saturated sets and the lattice of the Leavitt path algebra next class. This theorem is actually a very nice tool because it tells you that all possible graded ideals of the Leavitt path algebra can be retrieved by looking at all the hereditary and saturated subsets. And there is a bijection with every H, and each graded ideal is basically generated by that. And moreover, if you quotient I'm sorry, this is exactly the same thing. This is the ideal generated by H. I should have used this notation. The Leavitt path algebra. Okay. The quotient, now this is a quotient algebra. If I quotient the Leavitt path algebra by the ideal generated by H, I'm going to get another Leavitt path algebra. This time over the graph, the quotient graph that we have just described. So that was the reason of the construction. Okay? That's why it's called that. Now maybe I should give you the sketch of the proof. Basically what you do is consider the map. I want to show you that, actually give you this isomorphism. Consider this map subset in E, take a non-trivial one, and send V to 0 if V is in H, otherwise send it to itself. Send E to 0 if the range of E is in H, and to itself it's not in H, and similarly E star, send it to 0 if the range of E is in H, and to itself so these are the generators. If you next consider the show that all the relations, I'm just going to put the1, E2, the CK1, the CK2 conditions are in the kernel, are satisfied. Show that all these are basically sent to 0. So this is P1, etc. So once I show that, then last step is show that the kernel is exactly the kernel of this map. Yes. Answer. So we can first. Here's ask me for details, but via this brief definition, so if you define the phi on the generators and show that it's a algebra homomorphism, the kernel turns out to be this one, so they are going to be asked. Okay. Well, maybe I should stop here and continue. Well, let me give the definitions and also. E satisfies condition L because this is just if every cycle has an exit, it satisfies condition K if no vertex is the base of exactly one cycle. If a vertex is the base of a cycle, then there has to be another cycle that is based. That's based at there, which is a different one. And it satisfies MT3 or downward directed. Again, if for any two vertices U and B, there exists another path W that those two vertices merge at. Okay, they connect. A cycle is a cycle without K if any vertex on C is not a base to any other cycle. And finally, I define if for any vertex V and B is the set of the set of all vertices that V connects to. I'm sorry, no, it's the set of vertices who connects to V.
Set of sources of
Sources.
V, right?
V can be here. So there can be a path to W. These are the 1 and 2. V is already in there, so there's a trivial path there. But V1 and V2 are also in MV. All the vertices that connects to B. Yes, so there's the sources. Condition K implies condition L, which I'll use, but that's clear because if you have condition K, then there exists at least two vertices. If you have a cycle, there is another cycle there. So the other cycle produces an exit for the first cycle. So every cycle has an exit. Okay, why don't I stop here and I will continue next class with this. Okay, so we'll continue with some graded ideas. We mentioned about condition K. If the graph satisfies condition K, then we are extremely happy because then every ideal, the two-sided ideal, the Leavitt path algebra, is graded. So trivially, you can see that this graph, the KXX inverse, which we know has non-graded ideals, does not satisfy condition K. It has only one cycle, one loop, and it does not have a exit. Okay, it doesn't have condition K, so it has non-graded ideals. I'll come back there. Let me give you a few properties of the graded ideals before I move on. A graded ideal is graded if and only if it's generated by idempotence. Another nice property is the product of the ideals. This is extremely interesting. The reason being, as Professor Agaswamy mentioned, these are extremely non-commutative rings. However, they have this nice property that if you take two ideals, A and B, then AB is equal to BA. This is a general true for any two ideals. But the proof of this is extremely simple, so I wanted to mention that. If A is a graded ideal and B is any ideal, then the proof goes like, take a graded ideal, clearly the product is always in the intersection. And if I take X to be in the intersection, I'm going to show that it's also contained in A times B. Since A is a graded ideal, then I can find a local unit satisfying this property. And hence, X equals UX, so it's in the intersection, it's in the product, so the intersection is exactly the product. So we can prove similarly that the intersection A is BA, the condition is satisfied. Another nice property is the distributive property of any ideals. This is not necessarily true in any ring. However, in Leavitt path algebras, again, this works. Again, if you take one of the, this is true in general for any ABC. However, if you take A to be a graded ideal, then again, by the previous theorem, it's a simple corollary to show that A intersection B plus C is nothing but A times B plus C, which is AB plus AC. This is the intersection, and this is also the intersection from the proof of the previous theorem. So, simple, nice observation. C. And these rings are called arithmetic rings. The rings that satisfy this condition for every ideals, arithmetic. Okay, before I go on to the prime ideals, I will mention a theorem that says the generation I'll give you two characterizations of how to generate an ideal in general, not necessarily a graded ideal, but an arbitrary ideal. Let I be an ideal in math algebra. That this is generated by elements of the form U plus a summation of Qij R to the I times U minus summation of these terms. Where E is basically a subset, a proper subset of the vertices emitted by Q. So G is Ki's are the coefficients. U is basically a vertex. G is a unique cycle based at U. And RR is a positive. Okay, I just want to sketch the proof of this. That's why I needed this theorem to mention. If you look at this is how any particular ideal is generated, right? So, let's do this. Assume E satisfies condition K. If you look at the elements of the form, you have a vertex here and then a sum of a polynomial where G is a unique cycle based at U. Well, if you have condition K, you cannot have a unique cycle based at U because of condition K. So this term drops out. Assume it has condition K. Then there does not exist a unique cycle based at U. So any ideal is generated by, well, if this drops out, you have U times this element is nothing but elements of this form. Okay. Well, this is a homogeneous element of degree 0, and this is a homogeneous degree of element 0 as well, so it's the sum, so that's a homogeneous element. If an ideal is generated by a set of homogeneous elements, that means IISER greater. Conversely, let's assume, let's do this with the contrast. Assume A does not satisfy condition K. Well, the previous slide told us that if you have condition K, then it implies condition L. If E doesn't satisfy condition K, okay, I made a mistake in my proof. I said this implies this does not satisfy condition L. And then I constructed an ideal which is not.
You need to say that the quotient graph, that is a quotient which doesn't satisfy condition L. And then you are. that gives you a cycle without exits.
Right, and then I can,
Map onto X inverse, and that's one way of or your cycle today need to have an exit or not? You are generating elements in that. Those GIs
correct?
are they cycles without exits?
No, it's
No,
a
they
unique
just say
cycle
unique,
based,
only
no,
one.
it doesn't say.
I think, yeah, that's why you would then be no condition K implies there is a quotient graph
Does not have,
satisfy condition L. That leads to a cycle without exits. And you do not do
oh, okay, okay.
that generates a cycle.
So it does not
Which is not very,
satisfy K implies, which I didn't mention, but H, the quotient graph, does not satisfy condition L. Is that right?
yeah, of course, that exists.
So there exists a cycle, thank you, without exits. No exit. But the minute that you have a cycle with no exit, it's our famous example again. You can construct a non-graded ideal, like in the case of KXX inverse. Then there exists a non-graded ideal. Because again, you can take the cycle and the vertex and any polynomial on that cycle with no exit will generate a non-graded ideal.
That will be the question.
So that
The point is the property that every ideal is graded. When you mod out the graded, it survives in the quotient ring also. So when you mod out the corresponding Leavitt path algebra of that E/H, should have the property that every ideal in it is graded. But here you are able to get a quotient ring in which there is an ideal which is not graded. So that's a contradiction.
Okay. And so finally, I want to mention this characterization of a two-sided ideal, which I'll use in the last examples. Let E be finite graph. Now I need to draw finite sphere. I is a non-zero ideal of the Leavitt path algebra. Then I is generated by the hereditary saturated set that we have defined, because every ideal, recall, is when you intersect it with E0 is going to be hereditary and saturated subset of E0. It's generated by this and the Y part, where Y is the set of mutually orthogonal elements of what? J-I-G I goes on to N, where G is a unique is a unique cycle based at U. With no exit. In the quotient graph. And the second one is that Ki is non-zero or at least one. So this component is non-zero at some point. So you don't end up getting a vertex here. You have another case. One remark, so I is going to be generated by this H union Y. And if I is a graded ideal, that means the Y part is everything. That's the zero. So you don't have this. So this tells us how to look at the downgraded ideals as well. Now we can go. I'm going to mention the prime ideals. All of us know that an ideal is prime if the product of two ideals A, B in P implies either A or B is the P. There is a nice criterion to determine what are the prime ideals in the Leavitt path algebra. So after the theorem, what I'll do is basically look at some graphs and determine the ideals, which ones are prime, which ones aren't, which ones are graded, which ones aren't. So we're going to do a few examples from this point on. Okay? Now, the prime ideals, we're taking it to be a row finite graph again. P is an ideal whose vertices are denoted by H. Again, H is the hereditary saturated set. H is a prime ideal if and only if it satisfies one of these two conditions. Again, there is a generalization for every graph, but for the purpose of this talk, I took this for row finite graphs. P is generated by H, and well, we have realized that this is the case if P is a graded ideal, right? So this P is a graded prime ideal because it's generated by a hereditary saturated set. What makes it prime is if E0 minus H satisfies the MT3 condition or the downward directed condition. So this is, in the morning, Professor Ramaswamy mentioned about the prime rings. Zero ideal in a prime ring is prime. So that graph is zero. The graph itself satisfies downward directed condition, implies that the Leavitt path algebra itself is a prime. The second one tells us the non-graded prime ideals. So it has the H part, and then it has the part where it is generated by a f of c, where f of x is an irreducible polynomial in x inverse. C is a cycle without k. Recall, the cycle without k means this cycle C, any vertex on this cycle C is not a base to any other cycle. It's moreover, we want the quotient graph E0 minus H, the set of vertices of the quotient graph, to be MU. In other words, this vertex U is special because that is the base of the cycle without K, and the quotient graph is MU. So all the paths in the quotient graph end at U. They connect to U. And f of x is going to be an irreducible polynomial. If this is satisfied, then P is a non-graded prime. The first one is where P is a graded prime. So I'll leave this on the board. On the other hand, recall that we have this as, for any ideal, we know that it's generated by some polynomials of this form. If you look at this result with here. F of c is a polynomial that is basically, I can think of this as a polynomial which has a 1 plus, this is a polynomial, c is here. That's the cycle in this setting. And you have a polynomial where f of x has a constant term, that's where you see u here, plus, okay, I'll do my best, f of x is 1 plus a1 x to the r1 plus blah blah an x to the rn. So that's, and then you plug in the cycle into this polynomial, and that's what you get. So just to show you the equals. So however, this one is an irreducible polynomial. Okay, let's look at this example since it's already here, and try to find all possible ideas.
You can erase that stuff.
Everyone got the password and the photo
We can write it.
competition? Okay, we already have the computation of the hereditary saturated sets. I have 5 hereditary saturated sets. First, because of the theorem, I can write the all possible graded ideals. So, okay, I'll put a little graph here. You start with H0, you have H1, H2, H3, and the E0, right? That's the Hesse diagram for this guy. So I will have a similar lattice graded ideal structure. Well, this gives me the whole Leavitt path algebra. So let's just get rid of it. Okay, it's there, but I'm going to rewrite all the problem ones. The H3 generates an ideal. Then I have the ideal generated by H1. I have the ideal generated by H2. And the trivial one. Okay. Now let's see. Okay. Are these any of those prime? I have to look at, in order for them to be prime, I have to look at the quotient. Now, the graph itself, look over here, the graph itself, or if you subtract the empty set, you get itself, is it downward directed? What was downward directed, or MT3, same thing? If you have 2 vertices, you have to find a vertex, a common vertex that they join into. Well, one of them could be the answer as well. Okay, W connects to U, W connects to V. However, U and V, you cannot go from V to W. They're not connected. There's no path that they join in. So, well, E0 is not downward directed. Not empty. So, this is not a prime ideal. It's not a prime ring. So, let's look at H1. I look at the quotient H1, that's here. Is it downward directed? Well, I have 2 vertices, V and W, and if they both connect at V, so fine. This is prime. How about H2? Satisfied. Okay, they both This guy is MB. What is MB? Everything, every path here ends at B. This is E0 minus H. Over here, this is again MT3, and moreover, it's MU. Because W and U connect in here. Okay? And this one, well, you have only one vertex, W. W connects to itself. It's MT3, downward directed. It's 0. So that's prime as well. It's a prime graded ideal. That's a prime graded ideal. Okay, I have one not prime, not graded ideal. Proper ideals. Okay. I move on by the non-graded ideals. Realize that I have non-graded ideals, non-graded prime ideals. E0 minus H is going to be MU, where there will be an only one a cycle without K based at U. Okay. This is MB. However, none of those cycles is a cycle without K, because this cycle, B, there exists two cycles at this point. So I will not get any non-graded ideals from here. However, look at this one. Now this guy is MU, it satisfies this, and C1 is a cycle based at U without K. So there will be some non-graded ideals. Pick any irreducible polynomial in Kx x inverse and plug the C in. That's going to produce, well, let me put all prime spectrum. H3 is here, H1 is here. Then you have, for every irreducible polynomial that you pick, you're going to generate another ideal. 2 and 2 of C, etc. And there are infinitely many ideals here, all containing H2. And all of them are containing H2. That's it. 0 is not a prime ideal, so I'm not taking it to the prime spectrum. The blue ones, let's mark it again. Fi of x are irreducible polynomials in K x x inverse. Okay? So we have infinitely many. The blue ones are these non-graded prime ideals. Questions?
So, can you please again explain me that E minus H1 case, why that is downward directed? So I'm not getting that. Because for two vertices I have to find another one vertices as the
Which one are you talking about?
E minus H1 suppose. You said that
H1.
downward directed.
This one? No, okay. I took B and W, W and B. Which vertex do they connect at? B.
Okay.
Okay? So it's downward directed. There are only two vertices, and if I take two vertices, they connect at B. So it's downward.
So they are downward directed.
This one is not, because if I take,
No. triangle kind of shape you have made there. So, here.
You take two vertices, they have to connect. This vertex can be one of those. It doesn't have to be a third different vertex. If you take these two and if they connect here, these are connected at here. Any other questions? Of course, you have other ideals that are not prime that I can put on the spectrum, which are non-graded. Because if you take another polynomial and plug in the cycle there, that's going to generate another ideal, but it's not going to be prime. Only if the polynomial is irreducible, then it's going to be. In our famous example, I want to put somewhere, if there's another question, I will address this. This guy, if you look at the ideal structure here, there's only one graded, the graded ideals. Here will be the graph itself and 0, generated by empty set and the graph itself. You have only one vertex. So you have no proper except well. You have no non-zero proper graded ideals, but you have, if you look at the ideals, you have a bunch of infinitely many non-graded ideals. Namely, if you look at any, say, take irreducible polynomial, then the graded ideal have each polynomial generates since there are infinitely many irreducible polynomials, produce infinitely many non-graded polynomials. What is H here? So I'm looking at the second case. Every irreducible polynomial produces that. Well, H is basically the empty set. So everything is MU, that's correct. Everything is MD. You have only one vertex, and every irreducible polynomial will produce an infinitely many non-graded ideals. Is 0 a prime ideal? Is 0 ideal a prime ideal? Is this a prime ring? Is this a prime? Okay, is this downward directed? You have only one vertex. Yes, it is. Yes. Because V connects to itself, so it is downward directed. Again, if a polynomial divides the other, so you basically have the, this is nothing but the kx inverse. This is the spectrum of the kx. This is the prime spectrum of kx inverse. But you can pick up the same, the theory. Okay, well, I'll trace the board. I'll have you look at another example. Okay, this is another interesting example. You have an infinite graph, infinitely many vertices. Every vertex has two loops, and then vi plus 1, there is an edge from vi plus 1 to vi. It has condition k. If you have a loop, you have two loops. So all ideals are graded. So I don't have any non-graded ideals here. Look at the hereditary saturated sets. V1 by itself is a hereditary saturated set, right? Because I have loops here, so V1, V2 is another hereditary saturated set. So any hereditary saturated set is basically you chop the first n vertices, and that's a hereditary saturated set. Well, this guy is an infinite chain, and H1 is contained in H2, it's contained in H2, etc. So it's an infinite chain. So the lattice of graded ideals, which is the lattice of all ideals because you have collision, okay? All form an infinite chain here, which are generated by those sets. Hereditary saturated sets. And look at the quotient graph. Well, the quotient graph is just a copy of the original graph. You chop off the first n elements, and well, if you look at the E itself, everything is connected to V1. So it's downward directed. If you take any two vertices, definitely they connect at V1, but if you don't like that, they connect at the smaller one, whichever two vertices you take. So it's empty, free, downward directed on all that. So it's a prime ideal. All of these ideals are prime ideals. However, notice that there is no maximal ideal here. For every ideal, you can construct a bigger ideal. So it does not have no maximum ideal. But again, this is not a unital Leavitt path algebra. This doesn't. It has local units, but doesn't have identity. So, all ideals are prime. Let me do this first because it was so much similar. Now I change the orientation of the arrows. Again, the hereditary saturated sets, this time, in the previous one, recall the hereditary saturated sets were finite. Now they're infinite, because they are cofinite actually. So, if you start from any Vn, and you take everything after that, that's going to be a hereditary saturated set. Now again, they form an infinite chain, however this time, H1 is basically E0, H2, so there is no minimal. However, this guy, this produces the whole algebra, but this produces a maximal level. And then look at the quotient. If you look at the quotient, then, well, you get rid of everything. You have finitely many vertices left. So it's again downward directed. So everything is again fine. Just the orientation is there. However, this time there is the maximum ideal, which is this guy. But it has a nice chain again. Again, you have infinitely many primes. That's not wrong. back here, finish off, that's my last example. I have a finite graph. There are interesting things that can happen here too. It does not satisfy condition K. You have two loops here, however you have one loop here. So it doesn't satisfy condition L, condition K. Well, it doesn't satisfy condition L either. This cycle does not have an exit. So it will have both graded and ungraded ideals. Look at the hereditary saturated set here. Namely, take H to be V and W. Okay. That's a hereditary saturated set. Okay. Can't go back. It's a maximal ideal. Okay. The reason being, if you quotient it out with a maximal ideal in algebra, it is simple. Well, if I quotient L over Q, now from the theorem, get rid of B and W, what is the quotient? Q is isomorphic to the Leavitt path algebra of this guy. Well, this is the rose with two petals, so this is isomorphic to the Leavitt algebra of 1, 2. But Leavitt proves that this is simple. So we know that Q is a maximal ideal. However, we have infinitely many ideals here. All are generated by polynomials, irreducible polynomials. Now, they are all about zero is a prime ideal because the graph satisfies condition downward directed. Everything is connected at W. Let me put the graph here and move it back. Okay, let's see. That is U and that is U. Now, if you have U in your hereditary set, you have everything. If you have V in your hereditary set, then you have W. That's this one. If you have W in your hereditary saturated set, then do you have V in it? Yes, correct. You have V in it because you can go back to be saturated. So that's the only non-trivial hereditary saturated set that you have. Zero is prime because we said it satisfies downward directed in empty. And moreover, there are infinitely many non-graded prime ideals containing this. The reason being that, okay, we call the theorem, okay, that there are infinitely many irreducible polynomials and the quotient should be mu. Yes, if this graph itself, because H here is empty set, so this graph is MW, and there is a cycle without K based at W. Yes, it's this. So for every irreducible polynomial with KXX inverse, if you put the C in, you're going to get non-graded prime ideals. So the prime spectrum would look like this. Okay?
questions?
So somehow this description of prime ideals looks like some kind of dimension 2 type of condition. Like Zx prime ideals look like one irreducible polynomial in the prime element. Here also like a dimension 2 phenomenon, but otherwise it's like there is no.
The Kx inverse is the localization of Kx.
Because of
Kx. So that's a driving point.
Other questions?
Sorry, what's MT3? I just missed that.
Downward directed and MT3 are the same criteria. The C-star algebra is used MT3. I don't know. I don't know why MT3. It was shorter to write MT3 than downward directed. It saved some space, so I used that.
So we thank Müge again for her questions.